Sure. Okay. Thanks, Nanxin, for the invitation and the introduction. So hello, everyone. And my name is Boxin from Peking University. And in today's presentation, I would like to share something called NeurImg. So this is actually combination of two words. One is the neuromorphic type of cameras or imaging. The other is type of conventional or what we call the RGB imaging. And I will show some recent progress on combining this type of two cameras and images for computational photography applications. So what we are familiar with is this type of the frame-based camera, but we think they are problematic. Although it has been studied for like over 60 years, the problem is it has some redundant because the human brain or this kind of more advanced imaging technique, we believe it's not frame by frame. There's a lot of redundant information like the video, especially when it goes to high speed. And there are high latency, causes motion blur, and also low dynamic range. So the neuromorphic vision, this kind of concept has been proposed for many years until recently, maybe it's not really recently, from the year of 2005, Professor Toby Delbert, he introduces a DVD as a dynamic vision system, this kind of concept that really inspires a lot for inventing a new kind of camera. And later in his team in Zurich, they built this kind of first type of commercialized camera for the DVS and also the Davis, which combines kind of RGB, not RGB, this is a grayscale image. And later the color DVS, which has RGB information. While in Asia, in Nanyang Technological University, Professor Shoushen Chen and also his company in Shanghai, they invented CETIX, which is also kind of a neuromorphic camera. And later I will also share that in Peking University from 2018, we also invented this kind of camera called the VIDA. So let me give one example to have that intuition, what is kind of the neuromorphic camera. So maybe the most popular is the event camera. So they generated some kind of events anytime. So this is asynchronized at a pixel to see the change in brightness larger than a threshold. So here, instead of the absolute intensity, you should focus on the changes of the intensity, like the epsilon n and epsilon p here. When it exceeds a threshold or larger, increasing or decreasing, you will have this kind of events get pulsed in positive or negative one. So another intuition is you will see the blue, the green and the red edges here. This is a first commercialized neuromorphic sensor called dynamic vision sensor, DVS, in 2008. When there is no motion, like the background, there are some noise. But when the motion for the board, you will see how the edges of the board or the hands causes this kind of increasement or the decreasement of the signal. So here my group in Peking University, I call it camera intelligence. As actually we are doing interaction research of computer vision and computational photography. Especially for camera intelligence, I'm interested in combining unconventional visual perception or some new type of sensors. Either we buy someone or customize someone by ourselves. In the year of, this is not built by my own group. We have a big institute in Peking University working on this. There are some other professors who are doing these kind of vision chips. So in 2008, we invented kind of called spiking camera. This kind of mimic the way of how the human, so this one, let's see it again. So how the human brain senses the visual signal. We call it the VIDA. It's a kind of combination of VIDA and the RIDA. We have 40K FPS per second for this kind of spikes when its output exceeds threshold, and also it has high dynamic range. So when we have this kind of unconventional sensor, of course, we will have the corresponding intelligent visual computing. So this is what we do using computer vision techniques to build some camera prototypes that really can see higher performance with multiple dimension and less distortion. This is about image enhancement to remove the distortion than the conventional sensor to conquer the bottleneck of existing imaging system. So how the spy camera works, this is also very intuitive. instead of do the differential operation like the event camera or the DVS, what we do is the integration. So when we sense the accumulated intensity is larger than a threshold, we will fire a spike at the rate of the 40K per second, 40K per second. So what we can do is to capture very high-speed scenes. So the difference is that we already have this kind of accumulated signal. When we accumulate them together, we will have the image. This is probably one of the fastest moving objects we can capture in our daily life. This is our high-speed train in China, and maximum it runs at 350 kilometers per hour. So when we capture, or we were sitting on another train, actually the relative speed is doubles, it's a 700. We will have this kind of zero spikes. And in 0 and 1, when we accumulate them together, we will have a clear image of the high-speed train. Actually, this is a raw image. We will have a lot of this kind of reconstruction algorithm to make it look better. So this topic is about for adverse lighting for bad weather. So thanks to this kind of high dynamic range property or low latency property of this kind of neuromorphic sensors, either the event camera or the spike camera, what we can do is that if we have this kind of high speed and high dynamic range scene in autonomous driving, for example, especially when the car is driving out of tunnel, we will have much better more efficient observation. Like in last year in Europe, there's a company that's showing how this kind of detection for the pedestrian or for the car can be done in a more robust way under the extreme lighting conditions by using this kind of effective and more robust neuromorphic signals to low light, nighttime, glare, or shadows, whatever. So, but this kind of signal, it could be noise. And what we have studied more about image themselves. So starting from last year's CVPR, and in our group, we are exploring how to do this kind of drown filtering, so to improve the signal of the both sides. This is a collaboration with Ollie's group in Northwestern University. So we have talked about what we can do with the frame-based camera, what we can do with the event camera. Of course, they have different kind of advantages and disadvantages. So let's take a look at the advantage. So the event camera is high speed, HDR, low power, but the frame-based camera, it has very high resolution, and we have studied them for many years, so we have better control of the noise. So why not we build a hybrid system that takes a mutual advantage of these two types of cameras. So in this paper, we built a RGB data sets. It's actually kind of aligned data for both image and the events. With this kind of data, we can propose an optimization framework. This is optimization. There's no learning in this work. That takes the complementary information to do a lot of image enhancement, so that we can also serve for the downstream applications of what we call the GEF. I will explain it later. So first, let's take a look at how we capture the data. So it's very simple. It's just a very simple hybrid camera system that we use a beam splitter to synchronize the two types of cameras. So when the light comes in, it just gets splitted and arrives at the two cameras. But the event camera if you don't move the camera, there's no movement. Ideally, there will be no signal. So when we capture the data, we need to move the camera around so that we can get this kind of aligned RGB and the event signals. So here the red and the blue edges mean the increasement or the decreasement of the intensity changes. So when we get this kind of hybrid signal for the events and for the images, what we can do is called the guided event filtering, short for GEF, to get the filtered event frames and then for other applications. So in order to bridge these two types of signals, what we do for the GEF, the first step is do the motion composition. Why we need motion? So this is the bridge to connect these two types of signals, because we are observing the same scene. The scene is, or these two types of signals, they are connected using the latent motion field. On the left side, for the image side, we can calculate the optical flow by doing some math for the tidal extension, optimization. So what we want to emphasize here is this equation. So when we calculate how the motion varies against time. So it will finally become a QL, which is the motion or the optical flow field from the image side. So this is related to the image gradient and also the latent field when it times with the velocity. Velocity is how the object moves. So this is related to the events, which is somehow also related to the velocity of the object. So the xk prime here is the events that warped under this kind of velocity. So we can somehow align the event signals. So I will skip the details of this equation. So this is actually the event motion field calculated using the event signal. But somehow, anyway, these two will be equivalent to each other. And they are connected with the velocity, with the flow vector v here. So how to calculate the flow vector? So in CVPR 19, there is a method called contrast explanation. So assume that when we observe this kind of streams of event, and it should be related to the changes of the intensity, especially when the intensity changes at its its maximum speed. So when we draw this kind of warped event histogram, this histogram is related to the intensity at the fastest changes. But for our hybrid signals, we have both the event and the images. So we can build this kind of joint histogram, both the purple and also the green signal. The green signal is from the image intensities. So when we have this type of two signals warped together, we will have a joint histogram that is even more robust than using only event. So based on this kind of joint histogram, we can do the joint contrast maximization. So the inputted image event is the latent field. And what we can do is to calculate both this kind of intensity variation at the intensity level. So this is the Sobel filter, and this is from the event. So what we want to maximize is changes. So this is actually calculates the standard deviation. This means the output flow vector v that corresponds to the joint changes of the intensity and the event. So with this kind of velocity v calculated, so we can connect these two types of signals. We can do some motion composition to warp the event on the image domain so that we have the temporal gradient images in both domains, either in the event in the intensity domain that they are aligned with each other. So the intensity part is that it has higher resolution and also it's more robust to noise, so that we can use these two types of signals to do some joint filtering. This is similar. The concept is very similar to the guided filtering. Now we have the temporal gradient in both the QE and QL. We assume that QL, it will undergo some very simple transformation. The simplest one, of course, is a linear transformation. So we have the GA times QL and plus GB, then we have the GO. And the GO should be equivalent to the QO, sorry. QO should be equivalent to QE in this kind of optimization plus some regularization. So this is a optimization problem that can be solved by using existing method. So the filtered output will be the temporal gradient QL here. Yeah, like this. So let's see some intuitive results. So comparing to our existing this kind of the event signal and enhancement method, because thanks to the hybrid information, the GEF can get higher quality of the events. Or what we can do is also to do the super resolution, because QL is in a high resolution. We can do some sampling, and starting when it matches the resolution of the QE, then we come again to do the upsampling for each stage for the multi-scale, and finally we get the output like this to do the up to ×4 or ×8 super resolution. This is one of my favorite examples for this work. So this is a kind of bird in the lake in our university campus. So this is real data. When we move our setup to the lake, and we can capture you see how the outline of the bird gets very clearly reconstructed and super resolved, with much higher resolution. And this is another example when a car is moving inside our campus. So there could be some applications because this is the first type of this work. And if we get the purified our event signal, it can serve applications like the guided event for the future frame prediction, or this to interpolate the video frames using guided by an event. And for the motion deblur, event guided motion deblur, because the event quality got better, we can do better deblurring. So HDR, I will use another work to show even more beautiful result, but this is just an intuition. And for the high level, we show a very simple for the checkerboard. So even if this is a very simple example for the very salient features, if the event quality is not good, the tracking get lost. But if we get the event signal in a much cleaner way, so the tracking and detection will work even better. Yes, but someone will ask there could be some problem with our previous approach because we assume that the the image is good to guide the event signals, right? But actually, this is a dilemma. If the image is good enough, we don't need events. What we need events is when there is motion blur, when there is a high dynamic range, loss of the high dynamic range information. So using image to guide events only works if the image is good, the image themselves is good. So in this year CVPR, I think the students just finished a presentation maybe 2 days ago. This is an oral paper this year. What we call event zoom is to learning. This time is the learning approach to denoise and super resolve neuromorphic events. But this time we only use events. So after introducing the previous one, so you're basically familiar with the concept that's why we want to build these two kind of signals. Yeah, but the problem itself, we call it EDSR, is the event denoising and super resolution, because the event is not as good as a frame-based camera signal in terms of resolution and the robustness to noise. So EDSR is useful for many event-based applications, especially for this kind of adversary lighting condition. If the event signal is not good, the tracking, the detection will get lost. So here we want to use the event to get better themselves, to get the super resolved signal for denoise and for super resolution. This is another example. People do this kind of event-based image reconstruction if the event quality is not good, the reconstructed image also suffer from noise and low resolution. So the problem formulation, we also start from the image as a reference, because the image gets a lot of degradation during the capture. It can get some kernel. This kernel could be blur kernel, could be some noise, and it get downsampled. That's why we do super resolution, and of course, it has images. This is very clear for the conventional images. But for the events, it's a bit more complicated. But still, it should go some this kind of under degree degradation. We assume there is also some kernel for the original signal. It could be in a high resolution image domain, and it goes to some kernel for the noise and blur, and also there are some downsample. So we replace our event-based the image-based degradation model into our the ideal trigger model of the event signal. So, but this is seems to be a very ill-posed problem if we want to get the high resolution information of the events, which is here. There are some prior art doing this kind of event denoising called ED and CNN. It's used the MAU information to label the event and treated them as a classification work. The good thing is that if there are some wrongly fired events, it works well. But there are also sometimes there are lots of events. If there should be some events, but it not fired, it's not triggered, and this is something that existing event denoising cannot do. And also, I just introduced GEF. We also do the event denoising plus SR, but that heavily relies on the quality of the high resolution images and as mentioned of the optical flow to connect these two types of signals in two domains. It requires motion restoration and iterative optimization, which is time consuming. So this motivates us to, again, to investigate this problem in the low, severe noise and low spatial resolution for the event, and want to get rid of the reliance on the high quality images. We are inspired by our ICML paper called noise training. So sometimes you don't need the ground truth or the clean image. If you still have the noisy observation, you can still train a network to discover something from the noisy observation. So we built a multi-resolution event data set, starting from observing a screen that's showing something, the monitor that shows some the videos of different resolutions. We use the NSF data set. And then we can use an event camera to capture this type of images. Of course, we need some calibration, some very careful registration to make sure that they are somehow connected to each other. So this is just for observation. I mean, on the big screen here. So what we have for the data is like this. Then we have event signals triggered by images of different resolutions. So these event signals are also in different resolutions. Then we built a neural network to solve this problem. Actually, this is quite simple as long as we have the good data. The main structure is based on the 3D UNet, and the network incorporates additional 3D deconvolution layers for each scale of some scale connections. And what we have here is the E2I. This is a kind of reconstruction module. We have both the E2VID. This is the existing networks that perform the event-to-image reconstruction at the same resolution. And for the super resolution, we use an FSRCNN to perform the ×2 image super resolution here. Then what we can have is from the raw data to our enhanced data is like this. You will see how the edges get clean and how the noise in the background get suppressed. This is another example. So this is very interesting to observe. You will see that for the checkerboard, this is they're flickering, right? There are some data that actually there should be consistent. If we move the checkerboard slowly, there should be consistent increasement and a decreasement of the event. But the raw data, it gets lost. It's not stable. But when we get this kind of EDSR result, you will observe this kind of very clean edges moved in a temporarily stable manner. I will skip the tables to many numbers, but just want to mention one thing is that the existing, this is an open problem here. So the existing error metric for our event, the denoising performance of the event signal is not well defined because it will ignore the signals that are not fired. So in our group, I'm not sure whether there are concurrent works, but in our group, we are also studying this problem. We need a new error metric for and the ground truth data for evaluating whether the event is noisy or the denoised results get better. But here is a qualitative result. We have to already see the video, so I will skip this one. And of course, if we have the super resolved data with both denoising and super resolution, we will have better object tracking results. So we report some IOU number here, and of course for image reconstruction as well. So yeah, I will still give some time for introducing another work that we published. Actually, this is a concurrent work with the GEF. That's why when introducing the GEF, I say something very simple about the HDR. And at that time, because I'm interested in building a hybrid camera that can really capture the HDR information in a color and in high resolution, something different from what existing event-based HDR work has done. I will skip the background introduction. We know we are living in a real world that really have much higher dynamic range than our 8-bit camera that can sense. So here, this is something slide copied from very classic HDR approach used in some computational photography courses given to the students. Why I show it here, because we are inspired by this work, by this kind of multi-bracketing, is to find the valid exposed pixels. You don't want to use overexposed pixels. You don't want to use underexposed pixels. The simplest way, you do some threshold, and then you do the weighted average are using the exposure time, so that we can combine these images after tone mapping as a HDR image. And the existing solutions using either deep learning, we can do the inverse tone mapping. This is not, it's a challenging problem. And also we can use some non-conventional cameras. In ICCP R15, we have introduced a modular camera for the HDR. And of course, we can use neuromorphic sensors. But existing neuromorphic sensor-based HDR solution, they do not have color, and they don't use high-resolution images. So what we want to here is still use a hybrid camera system to combine these two types of information for HDR reconstruction. But this is kind of framework, or a unified framework, that we not only did design for the DVS, but also it works for our spy camera, which is called VIDA, because that one is provides more intuitive signals for the image reconstruction in the HDR domain. So what we propose for a new concept is called intense map. What I mean for the intense map here is something from neuromorphic signals. It can be reconstructed from the event data. You can use VE2VID or whatever image-based, event-based image reconstruction algorithm. But the good thing is that it contains high dynamic range information. Or you can use our spec camera to accumulate intensity, and then we get the integration. But both of them, they have no color. They are in very low resolution, like 100K pixels or something at this level, and it could be noisy. But what we have for the modern cameras, we can have tens of millions of pixels in very good color, but it will suffer from overexposure. Yeah, this is the key idea. We build this kind of NeurImg HDR network to combine these two types of signals together. One is I, is image, X is intensity map. So the pipeline, it actually follows exactly of what people do with HDR. We need to do something with color space conversion because that one has no color. We need to do the upsampling to match the resolution. And the most important is to do the luminous fusion. This kind of a follow the very classic way of doing the HDR, and we need to get the color back. Yeah. So for the upsampling, this is something we can do either by cubic or the pre-trained super resolution network. But the key idea is the luminous fusion. So in each domain, you will observe that here is oversaturated, but here the X upsampled X has some information. So we need a scheme to calculate the weights and somehow combine them as HDR information. So I will skip this one. So how we do is we build a network to do all these 4 steps. For the upsample, it could be very easy. The neural networks, the CNN, the convolutional networks, it's very good at doing this. So here for the weighting, to calculate the weight map, this is an intuitive example. So what we do here is add some attention mechanism to calculate the tension mask as a weight. And then finally, if we have the weight map and we have the HDR or the combined fused information in the HDR domain, we can get the color back by the IU and IV from that stage. But we find that color is not satisfactory. So we need another coordinate compensation network to tune the color in a natural way. So the system is actually the same as the GEF1, but here I show is our camera, the spy camera, so how it looks like. But we just replace the DVS with the spy camera here. And for the data, I will just skip this one. We have some synthetic data and evaluate on the real data. We can build a virtual camera to get this kind of observation in both the LDR image and an intensity map. For the real world data, for the Davis one, for the event, we run E2VID to get intensity map, but here you will observe some artifacts. This is due to this kind of Poisson reconstruction way of integrating the signal. But for the spy camera, because the integration is much simpler than the event signal, so the intensity map seems to be more robust. I will skip the numbers. Let's see detailed. This is using synthetic data. This is very famous data. So this is LDR image. You will observe a lot of large areas of the overexposure. And this is ground truth. And this is our readout. For comparison, they are all deep learning based methods using a single image. It's a little bit unfair. So we combine with a conventional approach that use two differently exposed images. But when the dynamic range is very high, combining two different exposure images is also very difficult to cover the entire dynamic range. But if the neuromorphic signal can get good observation, so it will have better results than this one. And this is result on the real data. By using the Davis camera, you will see how this kind of overexposed area get recovered. But again, so the artifact here is from the reconstructing the event signal, not from the algorithm itself. But for the spy camera, it has better results. But still, the color appearance have some space to get it even improved. So that concludes my talk, and thank you very much.
Yes, thank you very much, Boxin, for the very excellent talk. So, any question from our audience?
Oh, I see someone is typing in the chat in the.
Oh yes, there's some more question. Oh yes, that's actually from Wim. That's
Is it due to the low fill rate of the sensor regarding the flickering of the raw data? Which sensor do you mean? You mean the RGB sensor or the event sensor?
Wim, maybe are you still here, or probably you can refer ask directly using microphone if it's possible. Oh, yeah, I think the question has been wild, so you probably lose the context.
Maybe we can type later. I will answer the second question first. So like the Neuromorphic camera has a CMOS-based sensor. So this is something I'm not sure about how they implement the DVS camera, but for our spy camera, I should say yes. We've used very standard technology as what you can do with a very cheap CMOS sensor. Because all the sensor and like the circuits to control the readout, whatever, are designed in the university. We use very low cost some existing techniques. Yeah, it's very similar to what we can do, and very low cost what we can do using by building like a webcam or something like this. Yeah.
But for the Spark camera, that do you need to read out the pixel values at a random position, or like because some position maybe accumulate a value first, then do you need to read them randomly, or like how do you get out? I mean, for instance, rolling shutter, we line by line, like row by row, then we have a frame by frame for global shutter. But how do you read out the values?
Yeah, this is a very good question. Actually, someone is also curious when you binarize this kind of spike data at a very high speed. Actually, we have a lot of data redundancy. If you calculate the amount of data, it is not small actually. So currently, we read everything out, not randomly. Yeah, we need a very large space of storage, and it's not that fast. Yeah, we are improving this. Yeah, to make the even compact.
Finalize the signal first, then read it out. Oh.
Yes, and to the like 40K. Yeah, you can calculate it to a large amount of data. Okay. It's not compressed, and it's not easy to compress. So but just for research purpose.
But then it's quite similar to events camera. What is? Can you summarize basically what is the advantage and disadvantage, like the potential strengths and weakness compared to events camera?
Okay, so in terms of the I should not say advantage, but the design methodology is actually different. Like I showed in the last work for the HDR1, what we can do is we are more friendly to imaging. Although we also sense that this kind of emotion or this kind of very fast bit irradiance changes of a scene, but we have the quantized, this kind of 1-bit quantized signal. But when you just sum up them together, you get the image. But for the differential signal, you only have the -1 or -1, the +1. When you do the reconstruction, you need to do the integration. This kind of integration is more computationally more complex. That's why you need to solve a Poisson equation. But what we do is just to sum up them together. So in terms of the imaging side, it is more friendly.
Yeah, great, thanks. Is there a question from the audience side? Or? Yeah, I can also ask another question. That's why we're waiting here. So for this data stimulation, you have a big screen that you actually do you downsample the RGB image, then you re-record this as a low resolution events.
Yeah, we are actually simultaneously play a video with different resolutions on the screen and use them to trigger the event signal.
Okay, I see. But do you have? I mean, the resolution or the quality of this monitor, is this very crucial, or what type of screen monitor?
I think the resolution is fine because for the downsampled event, we only need like 100 times 200 or even lower resolution. Of course, we need to make sure that the resolution of the monitor or the image themselves should be subpixel level higher than the event signal. Actually the bottleneck is the frame rate or the refresh rate of the monitor. That's why at that time what I can find in my lab for the highest is a kind of gaming laptop that has the monitor has 144 FPS. Yeah, if we have a frame rate even higher, like 300, now I think we can buy some 300 FPS LED panels. Yeah, because otherwise the frame rate, the refresh rate, the monitor themselves is flickering. Then this will introduce other artifacts.
Yeah, that's
to trigger the event. Yeah.
I remember we also once try to record the screen. We also have this flickering effect. That
so you need to buy a more expensive one.
Something that we don't see with our human eye. Yeah, that's actually perfect. So